go quickly through
Okay.
the open ones.
Yeah.
All right.
So thanks, everybody. I'll quickly review where we're the introduction material. I think we have the here ones. So I want to start by laying out the steep precipitation gradient on the east side of the Mount Hood National Forest. Past research into fire regimes in on the Deschutes National Forest, the Ochoco National Forest really stopped at about 40 inches of precipitation in that Grand Fir, Douglas Fir zone. What's unique about this study is that it pushes all the way up into the Western Hemlock and Pacific Silver Fir zones that creep over onto the east side of the Mount Hood National Forest because it goes through a broad range of precipitation and climates in a very short geographic distance. The other interesting part of the east side of the Mount Hood is the really rugged topography that acts as a filter and modifies that climate and creates lots of different microclimates that are going to change the expression of vegetation and fire regime over time. Another important component of this research and as we consider the historical fire regime is indigenous land stewardship and cultural burning that was practiced by the Sahapin, Wasco, and Northern Paiute peoples who stewarded land in the Eastern Cascades for millennia. What I want to highlight here is that a lot of areas in the Pacific Northwest don't have an available record of cultural burning and how it varied in different forest types. But there's a fantastic paper that describes how burning practices for different cultural resources varied in different forest types or different forest zones on the east side of the Mount Hood. And it's also important to highlight this because the information I'm sharing with you tonight, we're going to be seeing fire scars on different trees and in different records. And these are culturally modified trees. This is part of indigenous history of land stewardship in the area. So it's not as simple as lightning and weather creating fires. There's a very human story to this. So I'm going to back up just a second. And in case you guys didn't hear it earlier, this project was developed in coordination with the Wasco and Hood River Collaboratives and also with the Forest Service. The idea here was to look broadly across the east side of the Mount Hood and understand the variability in historical fire regimes. And they wanted to go ahead and take a big slice across the whole area and understand fire across warm, dry to cool, moist environments. I also wanted to understand historical fire extent. So how big were fires and how did they move through the study area? When we understand the rate of fire and the severity of fire historically, we can use that to understand what the forest would have looked like. And then another piece of information that I'll talk about in a minute is we can use historical maps and records of what the forest looked like along with fire records to characterize how forest conditions and structure and dynamics varied in different parts of the study area. So on the slide right now, you're seeing red triangles across the east side of the Mount Hood. At each one of those red triangles, we have a fire history site. Whenever I do this presentation, I think it's important that we share terminology for talking about fire regimes. So just some brief review here. When we're talking about fire regimes, we talk about the magnitude of fire, and we use two terms to describe magnitude. Intensity is a measure of how hot a fire is, how high the flames are, how much energy is released in a fire. Severity is distinct from that in that it refers to what was killed or what was changed. So that's the effect of the fire's intensity on the ecosystem. We like to talk about the spatial characteristics of fire, including the type of fire. So was it a ground fire, a crown fire, or a surface fire? So which part of the vegetation is the fire burning through? Its size, of course, that's an easy one. How large of an area was burned? And then the complexity and patchiness within that fire area. So is it all burning the same way, or is it burning with different severity and different effects across its area? Some really important things that we're going to look at today, temporal characteristics of fire. What time of year was fire burning? and then how frequent was it burning. So just some general terminology there. And then I'm going to talk to you about different types of data we use for fire regime analysis. So talked about it a little bit, but dendrochronology is the use of tree rings, fire scars, tree establishment dates to characterize how forests develop with fire over time. The other part we brought into this project was historical documents. So this could be old writings and journals, it could be traditional ecological knowledge. And in this case, we used old timber cruises and historical photos to talk about what the landscape looked like in the early 1900s or late 1800s. For characterizing modern fires, we're usually using remote sensing. So basically, we're using satellites to quantify the size of fires and their effects. Just to review that, in this study for the two collaboratives, we focused on dendrochronology, the tree ring work, and then Kiala Hagman put together records of historical land surveys and timber inventories, and then looked at modern day fires and compared historical fires in those early records to contemporary fires. This is our east side of the Mount Hood National Forest Study Area. We ended up with 18 fire history sites. There's approximately 4 miles between sites. What we wanted to do was just lay out a grid across the area and sample it pretty evenly. The grid allows us to march across that precipitation gradient and sample different forest types, and it provides spatial coverage of a large area. You'll notice some of these sites are moved around or dodged a bit. That was because of limited access to some sites or wilderness areas. So in some cases, they've been moved to the nearest place we could sample. But in general, we just cast a pretty broad net to reconstruct historical fires. So from that sample of 18 sites, we ended up with 6 of them in what I would call relatively warm, dry forests. So forests where ponderosa pine is still the dominant tree today. These areas tend to have quite a strong or common Oregon white oak component. We had 5 warm, moist sites. These sites have ponderosa pine, but really grand fir, Douglas fir, and western hemlock are the dominant tree species in those warm, moist sites. And then we ended up with 7 sites in what I'd call a cool, wet environment that had Engelmann spruce, western hemlock, and silver fir as the dominant species. Really no ponderosa pine in these sites, some Douglas fir that we used to reconstruct historical fires. When I present this research, I really want to make sure everyone is clear on our methods. How do we come up with these fires, and how do we know they're fires and know the exact year that they happened? So I'm going to give you guys a little bit of background on methods in dendrochronology. So to start, we need to know a bit about the anatomy of tree rings. Conifers in the Pacific Northwest lay down annual rings. That annual ring consists of early wood, which is these wider light-colored cells, and then late wood at the end of the year, which is much denser, darker cells. And so late wood is laid on as the tree starts to encounter drought stress and basically shuts down for the year. So because trees make annual rings, we can go backwards in time and assign rings to calendar years. And that sounds like a pretty straightforward process, but trees often have false rings. So they add a ring or 2 rings in 1 year. And there's also missing rings present on trees. So it's not as simple as counting backwards. The other challenge we have is that we're sampling all of these samples come from dead trees. So we're taking them out of stumps or logs or snags. And in many cases, some of the snags and logs have been dead for well over a century. So we don't actually know what year we're starting at. So what we do is we use a process called cross-dating that relies on variation in tree ring widths to assign every single ring in a tree to an exact calendar year. So the discipline of dendrochronology was sort of modernized by this guy, A.E. Douglas, who was an astronomer in Tucson, Arizona. and they were building him in an observatory. And he noticed that the beams they were using to build the observatory had repeated patterns of tree rings. So you could look at one beam from one tree and it had the same barcode on it from tree rings that another beam had. And because he was an astronomer, he thought, well, this is maybe due to solar cycles. And so that was his theory, and he looked into it for a long time. And then he realized that that repeated pattern in those tree rings is really a function of climate. So we have dry years, we have wet years. This happens across a broad scale, and that lays a barcode down in trees. So by using that climate signature that's in every tree in the study region, we can take a section of wood from a tree that's been dead for hundreds of years, identify that tree ring signal either visually by memorization or with a computer that finds it for us, and we can take every ring and date it to its exact year. So just a slide showing you an example of that. On the right side of this slide, I'm showing you 3 tree cores dated from 1750 to 1760. There's a single dot on the year 1760 and 2 dots on the year 1750. And what you can see on those tree cores is that there's a very thin ring with very faint late wood in the year 1757 on all 3 of these trees. So what happened in 1757 is it was a dry spring followed by a really hot, dry summer. So you got a really thin ring, and the trees just shut down very abruptly during the growing season because they ran out of moisture. You can also see that the year 1755 and 1752 are very fat rings with thick late wood. So that's a year that had a lot of moisture. And so this is really just like a barcode. There's a pattern for every single decade. You can memorize this pattern, and that's how we're able to cross-date our samples. Just a shot here of the AccuGauge machine. We use this to measure every ring on every sample we collected. It's hundreds of thousands of rings just to do this project, and be able to leverage annually dated fire data. So at each one of our sites, we went to them and we removed cross sections from somewhere between 11 to 15 stumps or logs that had cambial injuries that are consistent with a fire damage. And we did this at all the 18 reconstruction sites. So just a shot of what that looks like. We're sampling out of stumps that are quite rotten, quite old, and you can sort of see what that looks like in the field there. They come out in many pieces, and then we have to glue them back together. This is a shot of finishing these samples. We've managed to put together some grants for some industrial wood processing equipment. This study was really the first time we got to use it, and we managed to process all the samples much faster because we had this equipment. There we go. So after we took those samples out of the wood and sanded them up, they look like this. And now you can see very clear and distinct cambial fire scars. So when we talk about scars on trees, there's all sorts of different agents that can cause a scar on a tree. It could be frost, it could be animal damage, it could be tree-on-tree violence. And they all have a different type of look when they cause an injury to a tree's cambium or the circumference of a tree. These are different fire scars on a tree, and I know they're fire scars because of how clean these injuries are. So what happened when this tree was about 8 years old, a surface fire came through and it killed the cambium on just the top part of the circumference of this tree. And then the tree was still alive on the bottom part of what's in the photo here, and it grew around and tried to seal up that injury. And then another fire came through about 5 years later, and the same process happened again, and fire scars started to stack up on this sample. So after we assign calendar years, we have fire years on all of our different samples that we can put into records for each site. I'm going to pass along one of these samples here that's in this photo from this study. You can sort of flip it back and forth. This right here is a fire scar. That's a fire scar. That's a fire scar. And I've written the year of the fire on the piece, and it sort of helps to flip it back and forth as you look at that. So that piece that's now going on the room is represented on the screen right now. So This graph on the bottom, it's basically just a timeline. There's a black dot on the left side of the timeline that indicates this tree was born in about the year 1660. There's a yellow timeline that shows its lifespan, and then the red triangles on that timeline correspond to fire scars. So every time this tree recorded a fire scar, the tree timeline gets a red triangle, and so that's a fire record for one tree in the study. So because we sampled many trees at each site, we're able to build a fire record using lots of trees. And that's really important. It gives us a second line of evidence that these are actually fires. So if you get an injury in the same year on several trees, the most likely process that would cause that would be a fire moving through a stand. So right there, I put a blue box around that fire from the last slide. That was showing you a record for one tree. And then you can see that there's several other trees we sampled at this site. Again, the red triangles are fires. And as you look up and down across samples, you can see that many of the fires were recorded on lots of different trees. So for example, there's a fire in, I think, 1776 that's recorded on 7 trees there at the sample site. So this is what I would call a composite record for fire at one site. So now I'm going to move into results for warm, dry sites in the study area. Again, these are sites that historically and currently are mostly dominated by ponderosa pine, and they often have a lot of Oregon white oak in the stand. So this is the dry end, places that get somewhere between 17 to 25 inches of precipitation, where we historically expect quite frequent fire. So at the top of this graph, you're seeing record for site EH15, and then there's a record for site EH19. And so moving across these 6 sites, what you can see here is a whole lot of fire at about a 10-year frequency at these sites. It's what we expect. We're in these lower elevation dry forests, but in comparison to other places in the East Cascades that are outside of the oak zone, this is a lot higher fire frequency. So if we were in the ponderosa pine zone in the Deschutes National Forest, for example, we'd expect about 15-year fire frequency. A lot of these sites had fire, especially EH30 had a fire about every 5 to 6 years historically. So I think that's a function of the production of surface fuels. So when you have oak litter combined with pine litter, you can burn a fire through that, and within a very short time, you're going to have fuels recover and you can move a fire through it again. So very frequent fire historically in these oak pine stands. Just an example of where those are on the map. So showing you an arrow to site EH15. But if you look at the graph on the right, you can see where these sort of hyper-frequent fire sites were within the study area. As you'd expect, they're generally on the east side of the study area at the lowest elevations. So conclusion for these sites, prior to 1900, there were 8 to 13 fires per century in these environments. So somewhere often less than 10-year fire return intervals at these sites. The next category I had were more moist sites. These are sites that receive around 37 to 43 inches of precipitation. These sites have often a significant component of Douglas fir and grand fir, so we're moving into that moist mixed conifer zone at these sites. What you see here is a couple different behaviors. So if we look at site EH12, it looks a lot like what we just saw at the hot dry sites or the oak sites. Same thing for EH24, but then if we look at sites 28, 22, and 27, they have more of an erratic period of fire where there's periods with lots of fire activity, but also periods that last over a century with no fire. So this is a really interesting property that we start to see as we move into moist forests. They have what I'd call a non-stationary fire regime, where there's periods of frequent fire followed by periods of over a century without fire. So a lot of times what fire ecologists like to do is to tell people a mean fire return interval. At sites 22 and 27, that becomes really difficult because the mean varies over time. So it depends on whether or not the stand is young and in a relatively flammable phase, or if it's in this phase where it's not burning very frequently. So Really interesting property. We've seen this on the Mount Hood National Forest on the east side, but also on the west side in Western Hemlock Forest, that their mean fire interval really doesn't exist there. You have periods with lots of fire in a century, and then you can have a subsequent century with no fire. So what's going on here? I wish I had a better map or figure for you here, but if you look at the landscape position of site EH12 and site EH24, those two sites are adjacent to the lower elevation drier forest that burned several times a century. And if you look at the position of EH22, 27, and 28, those sites are adjacent to silver fir and western hemlock forest. So they're a lot farther away from that frequent fire regime. So it seems that, you can have you can be in this precipitation zone of 37 to 43 inches of precipitation, so moist mixed conifer forest, and that really doesn't decide your fire regime. What decides it is your landscape context position. So who is your neighbor? If your neighbor is an oak pine forest that had fire in it all the time, you're likely to have fire all the time. If your neighbor is the western hemlock zone that has sort of this erratic pattern of fire over time, you're likely to have that erratic pattern. So summary for that, hopefully this puts it in better terms. Frequency in warm, moist environments may have varied with landscape position or adjacency to warm, dry versus cool, wet environments. Warm, moist fire history sites that are adjacent to warm, dry sites had 7 to 12 fires a century. Warm, moist fire history sites that are adjacent to cool, wet environments, i.e. a long distance from that ponderosa pine forest, had long intervals without fire and some periods with frequent fire. So a pretty erratic fire regime historically. I'm going to finish off with what we found in cool, wet sites. So we're now in the western hemlock and silver fir zone, with the exception of site EH18, which is a really curious place. High elevation, cold and wet, but a lot of ponderosa pine at that site for some reason. But as you look up and down across these graphs, you find a lot of shared fires among trees, and you again find that behavior where there's periods with 2 or 3 fires in 50 years, and there's also periods of up to a century or around a century with no evidence of fire. You can see that real clearly at site EH18 from 1550 to 1730. There's a lot of fire at that site, and then despite a lot of trees available to record fires, we didn't pick up a fire between 1730 and 1830. So something changed there in either the fuels, burning practices, or the way fire was moving through the landscape, that you see this really dramatic change in fire frequency. Again, I think so. Take a second here. So again, I think that historically fire frequency was quite variable in our cool, wet environments. In other words, there were long periods up to 100 years where we did not detect evidence of fire. There were also periods with much higher fire frequency where we'd find, for example, 3 fires in 40 years. This isn't isolated to the East Mount Hood study, and that gives me confidence that it's a real phenomenon. There's a possibility that we could simply be missing evidence of fire, so we didn't sample enough trees or the right trees. But we also find this on the Willamette National Forest, the Gifford-Pinchot, and the Umpqua National Forest when we're working in that western hemlock and silver fir zone, that there are periods with frequent fire and periods with infrequent fire. My best theory on what's going on here is that fire frequency is higher in young stands after they experience a high severity fire. So you get a stand replacing fire event and you move to very open conditions with lots of early seral fuels, and you also have the fuels coming from the stand that burns. So you have a lot of fuel there. You also don't have a tall canopy, so that means you're going to have much lower humidity, much higher wind speeds, and much higher temperatures throughout the year. So you have fuels that are abundant and conditioned to burn in those early seral forests, and so they support a higher fire frequency than a mature or old growth forest on the same site would. This isn't a new idea. It's certainly been looked at before. The idea that mature and old closed canopy forests on the west side or in these more productive forests have to experience much more extreme fire weather before they'll burn. But if you have an early seral forest, it'll burn under much lower or less intense fire weather and therefore burn more frequently. So I think that may explain why we have this erratic or uneven fire frequency over time in these moist sites. I also wanted to talk to you guys about a summary of annual fire extent over time across the study area. This sort of gives you a sense of how much fire is missing from this landscape in the last 100 years. So this graph, time is on the x-axis, and then on the y-axis, I'm showing the amount of sites that recorded a fire in a year. And I've labeled fires here that we recorded at several sites. So in 1693, 4 of the 18 sites recorded a fire. In 1854, 7 of the 18 sites recorded a fire. This is a really coarse look at fire size, but 3 to 4 sites has a land area of about 20,000 acres. So if you think about that, there's 7 to 8 fires in just the 1800s that covered 20,000 acres on the east side of the Mount Hood. If we look at the past 100 years, the biggest fire we have is the White River Fire. That's about a 20,000 acre fire. Historically, a fire as big as the White River Fire happened 7 to 8 times per century on the east side of the Mount Hood National Forest. What we saw in the data set is that fire years are shared across warm dry sites. So these big fires were typically burning the eastern half of the study area in the ponderosa pine and white oak zone. So for example, the 1854 fire burned EH29, EH30, EH25, all the way north to EH15. So it really was a fire that captured all of those lower elevation sites. That makes sense if you think about the topography. It's generally flat, and if you think about the fuels are going to be pine, they're going to be oak, and it's hot and dry there, so they're all going to get conditioned to burn at the same time, so you can have a big surface fire spreading a long distance in 1 year. But as that surface fire tries to creep up into the western hemlock or silver fir zones, it's going to start to meet fuel moistures that are going to extinguish it. So as we go into these cool moist sites, what you see are a lot of fire years that just occurred at one site. So say 1773, you pick up a fire at site EH17, but you never found a fire at any other site in that year. So that sort of suggests that fires in the cool wet sites were smaller historically. There must have been some limitation to them spreading and becoming bigger. And that limitation was probably having fuels that were dry enough to burn across a large area. But again, just to wrap up here, there used to be huge fires several times per century on the east side of the Mount Hood. And I guess I have another presentation. I don't think we have time for it, but the remarkable thing about those fires burning the dry mixed conifer in the ponderosa pine and oak forest was that they left old growth trees across that whole area. So when you look at where large and old trees were and where large and old stumps and trees are today, they're across that dry forest zone, meaning that those large fires historically were predominantly low severity, where they weren't creating big patches of high severity fire in the dry forest zone, big treeless patches there where they were generally surface fires. The follow-up to this work by Kayla Hagman looked at historical records of areas that were burned severely and were no longer going to be thought as timber production areas. And all of those were mapped in the upper elevation. So they were mapped in the cool, wet forest zone. So that's generally where our high severity fire was happening historically. And we had larger low severity fires in the lower elevations. So I've never done this sitting down, and I sort of lost track of a lot of where I was going, but I'm happy to take questions. And I think it'd be helpful to bring up some maps of historical fires and burned areas to sort of support that last topic of fire severity. Where was fire severe and where was fire lower severity? So yeah, happy to take questions and go back through slides.
How much can you tell what caused the fire? Like, whether was it indigenous people burning? Was it lightning? Was it something else? And the way to determine that.
Maybe
Yeah.
repeat the question.
So the question is, can you tell the ignition source of the fire? Was it a cultural ignition from indigenous stewardship or indigenous fires, or was it a lightning fire? That's a great question. Most of the time, if you're just using a fire scar as your evidence of a fire, you can't tell. So you have to use multiple lines of evidence to sort of sort out the contribution of indigenous stewardship in fire versus lightning fires. There's a few study areas where we've been able to do that and clearly see indigenous fire. And there's a couple lines of evidence that pointed to that. The first was that fire frequency dramatically decreased in the 1850s when there's forceful removal to reservations. The second is you can take a look at fire-climate relationships. So we generally expect fires to occur in hot, dry years. So in this particular study area, which is on the Umpqua National Forest, we saw fires occurring in cool, wet summers, which just doesn't make sense. And they only occurred in cool, wet summers until the 1850s, and then they stopped. So that's another way to look at it. Another way is you can simply graph the accumulations of fires in an area over time, and there's a slope to that accumulation, and then you can test for slope shifts. I think that it really matters what forest type you're in. So if you read the paper about Warm Springs, history and tradition of cultural burning, one of the main conclusions in that paper was the burning occurred in moist forests. The dry forests burned on their own in these big fires, and nobody needed to help them burn to produce cultural resources. But intentional burning was really required in the silver fir zone, western hemlock zone, moist mixed conifer zone. So I think if you go to those places, and you often see the shift to less frequent fire happening in the latter half of the 19th century. And probably you could test for fire climate relationships, and that would provide a second line of evidence of indigenous burning. Yeah, sorry, long answer there.
No, it's good. Thank you.
So this question relates to your last point about fire severity, and it's that if a tree is outright killed by a fire, it no longer participates in the dendrochronological record going forward from that point.
Yes.
And so do you ever encounter places where there's just like a dead end, like a massive tree kill? And I'm thinking of places like on the north side of Mount Hood at high elevation. There was a fire, and I think it was 2011, the Dollar Lake fire.
Yeah.
And you hike through there, and just massive tree kill as far as the eye can see. And so to me, that would just represent a dead end, dendrochronologically.
Yeah, excellent point. So brought up the cool wet site slide again to show you guys site EH17. And if you look at site EH17, you see this sort of floor for the oldest tree age. And you can see almost all the trees were established around 1610 at this site. So probably there was a high severity fire in the early 1600s that killed everything. And then you get what we call a cohort of Douglas fir establishing all at one time. So when we see that, that's good evidence that a high severity fire occurred. So we do see that generally when we get up into the western hemlock and Pacific silver fir zone, you start to see much more distinct cohorts. EH13 has one in about 1660. And there's one older tree surviving there, but there was probably a moderate to high severity fire there around that time. But yeah, when that happens, you can't go back any further in time to look at fire. Just want to contrast that with what you would see in a frequently burned site. So if you look at EH24 here, that's dominated by ponderosa pine and had a really frequent fire. Look at the inner ring date or the earliest ring on those ponderosa pine. It's a different age for every single tree. So in places where you have frequent low severity fire, trees are very uneven age. There's almost every tree is a different age than the next tree you sample. Places that have moderate to high severity fire clearly have these distinct age classes at them. Yeah.
How were you able to recover the tree rings from trees that were
600 years old from the 1400s.
Yeah, so there are, actually, the oldest tree we sampled, and so yeah, the oldest tree we got rings going back to the late 1200s. And we weren't even close to the pith on that stump, on a pine. There's simply some really old trees out there, and we're just cutting out of stumps, and then we find that they're 500, 600 years old.
That's
And
Ponderosa pine?
mhm.
I didn't think they even know that one.
It's rare to find them over 600. Every once in a while, we find one that's sort of pushing 800 years old, but it
What's
is
the
really rare.
California pine that's supposed to be the longest lived tree? How many years is that? Yeah.
Bristlecones can go 3,000 or 4,000.
Oh,
The oldest pine I know of is in Utah, and it's alive still, and it's 9 something. But generally pines 500 or 600 is really old for a ponderosa pine.
that makes me feel young.
Yeah.
Do you want to ask if there's anybody online, just tell them to shout, not shout, but tell them to
Yeah.
speak up. The chat's not really. good.
Speak up if there's questions online. I hope not. Oh, there's a chat. The sound is excellent. Okay, that's good.
That's an old one.
That's from a while ago.
I have a question while we're waiting. When you take samples, do you record anything about the orientation or the aspect or the slope or anything like that? Is that helpful information or?
Yes.
Is that lost?
No, so we do that at a site level, but we also do it at a tree level for the orientation of the scar and where the scar is formed. If you have a fire moving through a stand, say up in the uphill direction, typically a fire scar will form on the uphill side of the tree, and it's diagnostic of which way the fire burned. When you're in really flat sites, like a lot of the ponderosa pine sites, what we found is the same fire will be marked on multiple sides of the tree, and then the next fire will be marked in different places. So in some places it's diagnostic, in some places it's not, but we recorded it, and then it sort of became a wash with whether or not we could really tell the direction that fires came from.
How do you pick a good stump for aging? And they're dead, obviously, they're dead stumps, but as far as how rotten it is or might be.
It depends. So with a ponderosa pine, you can sort of look at the stump right away and know if it's going to have a cat face holding a lot of different scars. With Douglas fir, you have to blow the top off them with the chainsaw and clean them off, and then you can get a real clear look at the rings, and then you can make a decision on whether or not it's worth taking
So you
cross
make a
sections.
cross cut of it and get a good view with it.
Yeah, yeah. Douglas fir, record fire, you have to sample more of them to get as good of a record because they don't record fire as well as a ponderosa pine does. Just got to sort of do more work when you're
Well, pines are more resistant to fire as far as dying, I think. Don't they survive them better? Or?
I think that Douglas fir is more resistant to higher intensity fire. And that's more from sampling on the west side, but I've been in a lot of stands where there's char that's 20 to 30 feet up on these old growth Douglas fir. The stand obviously had a really intense fire, and a lot of these old growth Douglas fir survived. They get, 10 to 12 inch thick bark when they're really old. And so I think they're not as good at surviving fire as young trees, but as old trees, Douglas fir are up there with some of the most fire resistant trees out there.
Any of the area that you're studying, there's objections to logging?
Yeah, so we totally use that all the time just so we have access to stumps. Much of the lower elevation in that was high grade logged for ponderosa pine. So early logging, they were moving the largest and oldest trees. And so almost all of those are taken out, and those have the longest fire records. So when we go up into the sort of Douglas fir western hemlock zone, we usually pick a clear cut because that gives us lots of stumps to access and see. we did in this study was really focused on quantifying the rate of fire and the size of fire and contrasting them in different parts of the landscape. A follow-up to this would be coring trees and stands that have not been logged. So if you really want to talk about what that fire did and how it influences the development of a stand over time, you have to get out of the logged areas and you have to core trees. So we're hoping to do a phase 2 of this study on both sides of the Mount Hood National Forest, east side to west side, and add additional sites, but also go back to places we already have fire history, go to the nearest unlogged stand and see how the fires we've already reconstructed influence the stand's development history.
Andrew, at the end, you started to hint that I think some of the implications from this research, and part of the reason why the Hood River Forest Collaborative was really interested in this is because we're working with the Mount Hood National Forest to design forest management and restoration projects. And I guess I have a two-part question: is what happens when you have a landscape that is experiencing frequent fires and then you completely turn off fire? What are the impacts of that in terms of species composition and the structure and function of the ecosystem? And we're also obviously thinking about how we prepare our forests for climate change. So the second part of my question is, if we're entering a period that's going to be hotter and drier than average or what it has been, what does that mean in terms of how much more frequently we're going to experience fires, and are our forests prepared or not prepared for that?
Excellent question. So first part, changes related to removing fire on the landscape. Correct. And then second part, what does that mean for what's going to happen in contemporary forests? We might have teed this one up a bit, but I think the easiest way to characterize those changes at a landscape scale is to use Kiala Hagman's presentation for this same study. So Kiala used historical air photos that have been retaken from the 1930s to today, and then also these records of what timber inventories gave us of what the forest looked like in the early 1900s or the early 1800s. And so we can take this to compare the historical landscape to today's landscape. So this first shot, you're seeing a look at the higher elevation forest on Mount Hood there. And we know that had lots of fire in that cool wet zone, but those fires tended to be small. And so they would blow out patches of forest, and you can see that all across that landscape. You're probably not looking in the top photo. You're probably not looking at one fire, but the accumulations of decades of fire in that high elevation zone.
What's the date of that photo?
That's from 1933. So that's October 22nd, 1933. And then the bottom photo is 2015. And so you can see that high elevation zone used to be more of a mosaic of different stand ages with holes in it from recently burned stands that hadn't experienced a severe fire in quite a while. And now it's much more homogeneous across that area. So we've removed those smaller mixed to high severity fires out of that upper elevation zone. So that's one example. Let's see if this it's not letting me. There we go. So I'm going to sort of skip the details here, but this map on the left is showing you several different historical surveys of the east side of the Mount Hood taken at different time periods. So mid 1800s all the way up to the 1930s. And the surveyors were interested in mapping areas that had been burned over and wouldn't be useful for timber production or forest management in the near future. So they're not saying every tree has been killed, but they're saying most of the timber has been burnt up by fire. And so it's a combination of different perimeters where they said this area is burned up. And what you see in this photo is a clear pattern that higher severity fire is towards the west side of the landscape at the higher elevations. And you don't see those big patches at the lower elevations. So having frequent, large, low severity fire at the low elevations prevented these big patches of high severity fire from happening in the dry mixed conifer and ponderosa pine zone. But historically, they did happen in the upper elevation forests and burn forest to the ground, essentially. So that is the pattern then. This is the pattern now. We're missing our small high severity fires in the upper elevation forest. And not so much on the east side of the Mount Hood. The White River fire provides an exception, but we're starting to see bigger patches of high severity fire in lower elevation forests. So if you look at the Deschutes, if you look at the Freewind, they've had huge fires, put huge stand replacing patches in dry forests. So how does removing fire relate to changes in forest structure and composition? These are 1930s timber types. So we have a pine mixture. It's 20 to 50% ponderosa pine by volume. That's what we'd sort of call a mixed conifer stand today. Ponderosa, those stands are mostly dominated by ponderosa pine and then pure ponderosa. And if you look at this landscape in the 1930s, the area that's dominated, or at least in that ponderosa pine type, goes way up. So it goes way up into the mixed conifer zone because fires making ponderosa pine the dominant species historically. Now, if you look at a then versus now comparison with the same map, this is that 1930s map showing the ponderosa dominated forest going way to the west. And if you look at it now, it's restricted only to the hottest, driest environments. So Grand fir, Douglas fir have essentially expanded downhill into the dry forest zone. It's not just fire exclusion that does that. Other factors that were really important were the high grade logging of ponderosa pine. So if you come log those trees, remove the seed source, but more importantly, you disturb the soil and you already have Grand fir and Douglas fir there, they're going to move into that situation and take advantage of it. The other factor, and I don't know the extent of this in this area, but other areas in East Side, late 1800s, just incredible numbers of grazing animals on the landscape. They're going to graze the bunch grasses, and bunch grasses are fantastic competitors with tree seedlings. But if you remove all that competition, the tree seedlings do quite well. So you have three things coming together there. You have early logging, you have fire exclusion, and you have really heavy grazing, which conifers really appreciate that type, those disturbances to have forest seed in. So pretty dramatic difference in the then and now in forest composition. So the last, I'm happy to share this full presentation and Keala's report with everybody, but the follow-up to your question there, what does that mean for now? It means we're at risk right now for having larger patches of high severity or stand replacing fire in the dry mixed conifer and ponderosa pine zone. We might be a little bit worried that when we have a high severity fire at upper elevations during extreme conditions, that those patches might be bigger than they were historically because we don't have that landscape mosaic that was there in the 1930s. Another concern is that species like Grand fir growing in the dry forest zone or the ponderosa pine zone are not resilient or resistant to insects, disease, and drought in that zone. So a lot of work in the 60s to 90s, they were taking these sites where we had logged out ponderosa pine, and they were saying, okay, the future crop here is going to be Grand fir because it's moved in. And so we want to understand how we move these Grand fir to the production phase. And by the early 90s, they said, this has to stop because the Grand fir keeps collapsing. Every time we hit a drought, they get hit by fir engraver and a lot of other disturbance agents, and they just aren't suited to be on sites with less than 32 inches of precipitation. So we have this massive shift of tree species downhill into an environment where it can do quite well during cool, wet times, but you hit a drought and it sort of collapses all at once. So in terms of having tree structure, carbon on a site long-term, ponderosa pine is much better adapted on those dry sites. And so that's a long-term consequence of the way things are composed now.
Is white oak more resistant to fir or same, not roughly, or
Fire resistance or
survivability after the fire?
I think it really depends on the forest structure and the white oak. So white oak can grow in sort of a really shrubby stand, or they can grow into these large trees. And that's a question from the East Cascades Oak Partnership that they're really interested in why do we see these different expressions of white oak? Sort of
That was
white
my
oak,
next question.
yeah,
What
so,
determines whether it's a little scrub oak this tall or a magnificent tree?
yeah.
Like trunk this big?
So I think two different strategies there. This is not supported by data, but my hypothesis would be if you have a lot of surface fuel and more intense fire when it comes, that's going to support a shrub type community. If you have really frequent fire, that's going to kill seedlings, but be at much lower intensity and severity, you might develop larger oak trees in that setting. But it also could do with soil and a lot of other factors.
Soil and nutrients is a big driver, like they
Yeah.
grow them huge in the Willamette Valley, in part because there's so
They
much.
can do it.
Yeah, it's so productive.
Well, and here just in the hills east of the valley here where I live. They grow, it's all together, it's pine, fir and white oak are growing in a forest, multiple, they're in tight too.
Yeah.
And sometimes the oaks grow straight up because they're in competition with sunlight, they grow straight up like a fir tree,
Yeah.
they take on a different form.
So probably we should wrap up.
Sorry.
No. Yeah,
Are there
it's
any,
fantastic.
Any other comments online? Or chat, maybe?
Any last questions from folks online?
Yeah.
Yeah, we may have just shut them off.
I still saw 13 participants, last, if you want to
I have
stop
one more
sharing.
question, I'll wait until
Yeah.
that.
Yeah, if you want to
It's a
stop
quick one.
sharing, Andrew.
Yeah. Um, there's a lot of. I think this will bring them back up.
Yeah.
There we go.
Yeah, they're all still there.
They're all sleeping there.
Of course, you don't know if they're actually still there. It's just- Logged on.
All right, we gotta thank you.
Cool. Thank you guys in the online audience too.
Yeah,
Okay, all the private
here.
yeah,
One more question. All the private companies, timber companies here, I will say, are planning a preponderance of tamarack or western larch. And I know it's because they're more disease resistant, but, or what is the reason?
Western larch is another tree that I would say is up there. Even more so than Douglas fir and being very fire resistant too. So it's not necessarily, it's a strong choice for fire resistance. That I think, and they probably know more about it than I do, but my experience is you need to have sites that are much wetter and more productive to grow larch in some way. So I typically find old larch in these wetter areas or wetter into the spectrum. So.
No, there's gonna be a lot in 50, 60 years, there's gonna be a lot of, I hope there's a market for it, because they're planting a lot of it. And some's coming back on its own too.
Okay,
round of
well,
applause.
thank you very much.
Yeah, thanks for
Yeah.
having me.
Presentation, really interesting. Hope the folks online